not so far back, he was from here. We will be talking about Weyl metrizability of three-dimensional projective structures and CR manifolds. So, please, the floor is yours.
Thank you. I'm very thankful for the organizers who are allowing me to speak in this wonderful training school workshop. So yeah, my main topic has to do with metrizability, Weyl metrizability in particular. Let us start with what we heard this morning, although not quite in this form, but we'll get there, what Boris was talking about. A projective structure on a manifold is a set of torsion-free connections with geodesics coincide as unparameterized curves. So if two connections belong to the same projective structure, that means they are related in this way for some one form beta. We call projective connection metrizable if there is a pseudo-Riemannian metric G such that the Levi-Civita connection of this metric belongs to the projective class. So these geodesics are geodesics of some pseudo-Riemannian metric for certain parametrization, and we call it Weyl metrizable if there is a representative in this projective class such that it satisfies this relation for a some one form beta and a pseudo-Riemannian metric G. So this relation means that in fact this connection preserves the conformal class of G. So if you change your G by multiplied by a conformal factor and change beta in this way, then you would see this is also satisfied. So more explicitly, you can define this sort of linear connection in terms of this G and beta using this relation where this is the Levi-Civita connection of G. So in other words, knowing this, we can easily see that Weyl metrizability means that there is a conformal class of metrics such that this there is a representative connection in the projective class that preserves this conformal class. So it's not like a Riemannian metric, but it preserves a conformal class. That's Weyl metrizability. And Weyl metrizable connection obviously is metrizable locally if this one form beta is closed. So locally you can write it as d of some function, and by conformal scaling you can actually find a metric in this conformal connection of conformal class of G such that this the Levi-Civita connection of that metric belongs to the conformal class, to the projective class. So this is the definition of Weyl metrizable that has to do with existence of a conformal class of metrics, and metrizable is just a metric. So Weyl metrizability does not imply metrizability. So now we would like to view this Cartan geometrically, formulate this. As Boris talked about, the projective structure is a Cartan geometry of type SLN and the first parabolic, where Q1 is the first parabolic being the stabilizer of a line in Rn plus 1, or a point on the sphere. And it can be written as some G0, the reductive part, and the Heisenberg part, Q plus. So you can think about it as a quotient space, SLN plus 1 over Q1, and deform it sort of locally. This is what we can think about it, Cartan geometry. So the homogeneous model is SLN plus 1 over Q1. A conformal structure of signature PQ also is a Cartan geometry of this type, where P1 is the first parabolic, meaning the stabilizer of a null line in RP plus Q plus 2. And so we saw these things this morning, and we're going to hear about it more later on. So given a Cartan geometry, a Weyl structure, so we have this, in these cases, we have these principal bundles, and define G0 to be the G0 principal bundle. So the base is M, your manifold M, here and here, and the fibers are G0. So there's a clear projection of your principal bundle to this G0 principal bundle, meaning the quotient by the Heisenberg part. And a Weyl structure is basically a section of this form from this G0 principal bundle to G, which is G0 equivariant. So if you remember the definition of the Cartan connection, we had this equivariancy condition, and we would like this to be to remain valid. So this is a definition of a Weyl structure, and it can be done for conformal structure, for projective structure, for CR structure. And so these are all conformal structure, projective structures, are all Cartan, some type of Cartan geometry. And for simplicity, we're going to call Weyl structure for a conformal projective CR geometry. We call it conformal connection, projective connection, CR connection. So this, now we can easily reformulate what we saw previously, is that a projective connection is Weyl metrizable if there is a conformal connection, meaning that a Weyl structure of a conformal geometry, we denote it like this, for some C is some conformal class, such that this conformal connection belongs to is also a Weyl structure for the projective structure that we have. So belongs to this equivalence of torsion-free affine connections. And it is locally metrizable if and only if the skew part of the Ricci of this conformal connection is vanished. This is again a kind of equivalent way of saying what we saw in the previous slide. So let's see what are the results on Weyl metrizability in dimension 2. So let's just do some counting. Local generality of two-dimensional projective structures is given by two functions of two variables. That is, you have four Thomas symbols and you mod out by diffeomorphism, so you end up with two functions of two variables. Local generality of two-dimensional pseudo-Riemannian metrics using isothermal coordinates is one function of two variables. And local generality of 2D Weyl structures depends on two functions of two variables. In your analytic case, you can check Cartan-Kähler. So this easily says that by just looking at the generality, that for metrizability, there is local obstruction, because you have one function of two variables, and here projective, there are two functions. So not all projective structures are metrizable, obviously. But then for Weyl metrizability, at least the generality looks the same. So it's not clear whether there are obstructions or not. So Brian Dunashki-Eastwood in 2008 gave necessary and sufficient condition in real analytic case for the metrizability of two-dimensional projective structures in terms of components of any representative of the projective class. And in 2014, Mettler showed that in fact, any two-dimensional projective structure is Weyl metrizable. And sort of one of the main observations he made is that in 2D, you can look at the make a one-to-one correspondence between conformal connections in this projective class and holomorphic curves defined by the sections of the twistor bundle. So if you take a holomorphic, so the twistor bundle, four-dimensional twistor bundle, we're going to see it later on. I'm not going to elaborate on it in this slide. So the fibers are disks, holomorphic disks, and any section of this bundle, holomorphic section, so this here has a canonical integrable complex structure. Any holomorphic section gives a conformal connection of the projective class defined on N2, and in fact defined this conformal complex structure on the twistor bundle. And in fact, the existence of this holomorphic curves because is just unobstructed, because this is a complex surface over a complex curve, so you can, by using holomorphic coordinates, there's no obstruction. Locally, you can always take a holomorphic section. So every projective structure is Weyl metrizable because there is no obstruction in taking a holomorphic section. And also he showed in 2021 that metrizability is equivalent to this section that we obtained here being pseudo-holomorphic with respect to an opposite almost complex structure, which is never integrable, unlike the other one. Well, so we won't deal with this part, but it's kind of interesting if you want to derive this second part in Cartan geometric language. You run into difficulty. It's not quite clear to me how to do it because this non-integrable, this second almost complex structure is not really projectively invariant. So it's an interesting to give a rederivation of this result in Cartan geometry. But the first part is clear. So we want to now deal with three-dimensional case. Again, let's do a quick count. So three-dimensional projective structures, by considering the Thomas symbols and mudding out by diffeomorphism, it's 12 functions of 3 variables. Three-dimensional conformal structures depends on, again, count the metric components, mudded out by diffeomorphism and scaling, 2 functions of 3 variables, and Weyl structures. So you have also the Weyl 1 form, and its exterior derivative in dimension 3 has 3 components. So it turns out it has 5 functions of 3 variables. So there's clearly an obstruction for both metrizability and Weyl metrizability in dimension 3. Now, if you want to give a complex geometric interpretation of Weyl metrizability, there are 2 ingredients. One of them is Lebrun's kind of Pfefferman construction of 5-dimensional non-degenerate CR structures from 3-dimensional conformal structures. The second element is a 7-dimensional 2 non-degenerate CR structure on the twistor bundle. So this twistor bundle is the twistor bundle of a correspondence space of a 3-dimensional projective structure. So this has been observed generalizing, many large class of parabolic geometries by Gregorovich, and we kind of came across it in a work with Kruglikov, sort of on only in this specific case that it sort of is a straightforward generalization of Atiyah Hitchin-Singer twistor construction. So the aim is to express Weyl metrizability of 3-dimensional projective structure as certain 5-dimensional non-degenerate CR submanifolds of this 7-dimensional 2 non-degenerate CR structure. So you want to find like a section that is sort of transversal to the kernel of the Levy bracket, and with certain properties. That's main goal. So let's look at this Lebrun's Pfefferman construction. So a 3-dimensional conformal structure is of this type. We are focusing on Lorentzian signature because this conference also involves physics, so why not? Then you can see that the structure group is CO12, and let's try to view it as GL2 up to a cover, and we don't distinguish between negative and positive scaling for now. And so the structure group acts on the coframe, and if you take like the most natural, this would define via the action of GL2 induces an almost complex structure on each tangent space of your 3-dimensional conformal structure. So now you have one almost complex structure acting by using the induced GL2 action, and its stabilizer is a subgroup of the structure group, which is CO2. So this allows you this is one of the advantages of using Cartan, is that immediately you cook up what people in this twister community especially are interested in, which is the twister bundle of a geometry like this. So you know what the stabilizer is CO2, therefore you can cook up a sort of a description of the twister bundle, which is the space of all almost complex structure. And it's basically your principal bundle quotient out by H, where H is basically this CO2 times the Heisenberg part of the parabolic, so it's of this form. And therefore the fibers, if this is your twister bundle, so it's a 5-dimensional manifold, And so it's a 5-dimensional manifold fibering over your 3-dimensional conformal manifold, and the fibers are P1 mod H, where P1 is the first parabolic, H is the sort of stabilizer of this almost complex structure, and you would just immediately see that it's equal to CP1 mod by RP1. So this twistor bundle can be identified with another interpretation by the projectivized time-like one forms. So here, this is like a collection of two disks, and here, if you the time-like also because we forget about scaling, so the time-like bundles are also you can identify it with the two disks in here, and this sort of description was given also by Sato and Yamaguchi in a larger context of the so-called Lie contact structures, where in this particular case for 3-dimensional conformal structures, in fact, coincides with Lebrun's CR structure.
Omid, CP1 minus RP1, right? Cool.
Yes, sorry. Oh yeah, right. CP1 minus, this is not mod, minus. So you take out the RP1. So it's a collection of two disks. So here we've cooked up basically what first in the twistor community, in particular a paper of Lebrun, and Lionel Mason's thesis was also involved in this. We're interested in, and so let's analyze this a little bit further. So let's put the Lorentzian metric in this form. So this is our Cartan connection. It's a one form with values in SO2 and we express it this way. So this has to do with what Boris was talking about. This is the G minus part. You can identify it with the tangent space at each point. This is G0 and this is G1. One grading of SO2 And so in this twistor bundle, this omega 1 the kernel of it would give a contact distribution of this 5-dimensional manifold, and the holomorphic contact distribution in the complexification of the contact distribution is given by the kernel of these 3-1 forms, where they're written this way, right? Where theta 1 and theta 2 are elements in your Cartan connection. And you can see this, you can immediately check that this sort of complex valued Pfaffian one form is integrable. So by Newland and Nuremberg, you know that the complex structure is integrable, so we get a CR structure of indefinite signature. So Lebrun gave a characterization of this 5-dimensional CR structures arising in this way, but it's kind of a little bit global because he assumes that it's like foliated by CP1. It's not quite local. Apparently, Mason has like an incomplete characterization. There is apparently a local characterization, according to Mason, by Robert Bryant. I mean, this is not really what I'm going to talk about, but the inclusion of, so if you view CO21 as SP4, and the Pfefferman construction gives an inclusion in SU22, this suggests there is a characterization via the existence of a parallel 2 form on the CR structure. And this 5-dimensional CR structure, which might actually help sort of extend sort of a tractorial characterization of this Pfefferman construction that is going from a conformal structure to a Lie contact structure. But this is for not quite what I'm going to talk about. What I would like to say is that first let's look at this is what Boris probably wanted to talk about this morning, is that when we have a conformal connection, so the next thing is to find a Cartan, so this is the Cartan connection. Cartan curvature would be sort of the deformation of the Morar Cartan forms. So if the conformal structure is flat, this would be sort of Morar Cartan forms and it's equal to 0. But if your conformal structure is not flat, you would get obstructions here for some 2 forms, zeta, psi is 0 to psi 2, where they are written, there are 2 forms that are in terms of omega I, your semi-basic one forms, for some coefficients A0 to A4. And these 5 functions on your principal bundle are the so-called define your Cotton-York tensor, which you can actually put as a binary quartic, where for some lambda, where this lambda takes value in real and infinity, and you can view it as sort of an obstruction to the integrability of a null plane in this Lorentzian structure, conformal Lorentzian. So this is sort of, you can view it, this is the fundamental invariant. This you can, your Cotton-York tensor, if it vanishes, then you know your conformal structure is flat. So this is sort of a glimpse at the Cartan curvature of a three-dimensional conformal structure. So what actually is interesting for me is that the same thing can be said. So now we have a three-dimensional conformal structure, a five-dimensional CR structure. So a three-dimensional conformal structure, its fundamental invariant is a binary quartic, the Cotton-York tensor. The same is actually true for a five-dimensional CR structure. It's, again, fundamental invariant is a binary quartic. And what's interesting in this proposition is the main observation is that the binary quartic of five-dimensional Lebrun CR structure is type D, type N, meaning that such CR structures that arise from a three-dimensional conformal structure, their fundamental form has a repeated root of multiplicity 4, or they can be 0. So let's see how to prove it. The proof is quite straightforward. So let's just view, this was the Cartan connection for three-dimensional conformal structure. View it as a subset of SU22. So this is how it is. So you can see I rearranged things where omega is just omega 1 plus I omega 2 here. And this is your contact one form. So this would be your contact one form in the CR structure. This would be the holomorphic part of the contact distribution, anti-holomorphic part. This would be your G0 for the conformal structure, CR structure. And you will see that G0 is supposed to be SU1, CU11, but in fact it's not. Here it's reduced. This part is reduced, so one of the off-diagonal parts of the SU2 is reduced. And note that the indefinite metric on the contact distribution is of this form. So this is your holomorphic part, anti-holomorphic part, and this is sort of your Hermitian metric on the contact distribution, and your G0 is reduced, the structure. This is some main observation that would help exactly up to. Once you know this, then it's immediate to use the expression for the binary quartic of the CR structure related to the binary quartic of the Cotton-York tensor here, and show that the binary quartic, in fact, for this one is type N, is a repeated root of multiplicity 4. And again, this is again a quick flash of how the Cartan curvature looks for CR structures. So this would be your SU22 valued Cartan connection. This would be your Cartan curvature. And sort of these two forms, they involve, entries they contain the entries of your binary quartic. And which I'm not going to write down because it's quite messy. And again, I'll remind you that this is the form of the Hermitian symmetric on the contact distribution. And once you have this Hermitian symmetric, you would see that Q, your binary quartic, obstructs integrability of Lagrangian null two planes, which are of this form. So once you know the Hermitian symmetric of this form, and Lagrangian null two planes all of them can be written this way for parameter lambda in R and infinity. So this is like taking value in P1. And if such one plane of this form, a two plane of this form is integrable, then you know that lambda, for the choice of lambda, which makes this, for which this is an integrable two plane, would be a root of that binary quartic of the fundamental invariant of the CR structure. So clearly, we know by Lebrun's construction, we have a three-dimensional manifold, the five-dimensional manifold fibers over three-dimensional. There's clearly a fibration, and which is also Lagrangian null two plane. So there's clearly a root, but in fact, this root is a repeated root of the binary quartic of multiplicity. So this is the main observation. And right, any questions so far? So far, I just sort of a feature of this Lebrun CR structures that I'm going to use later on. Now I would like to focus on three-dimensional projective structures. And so there is a correspondence space. So you have if you have a three-dimensional manifold with a projective structure, look at its oriented projectivized cotangent bundle. So this is sort of a so-called correspondence space that was studied by Takeuchi in '94, and this space, oriented projective cotangent bundle, has an induced structure that is referred to as with many names, but we are going to refer to it as an almost para-CR structure, meaning that it's the following: that at each point, let's say x, at the point x of M and a projective class of one form, the tangent space of N at that point has a contact distribution, and that contact distribution, it's a five manifold. This thing is a five manifold. Has a splitting into two rank 2 distributions that are also Lagrangian with respect to the induced symplectic structure on delta. So one of these, this V, is obviously the vertical, because this guy fibers over M, and the fiber of rank 2. So M is three-dimensional, this is five-dimensional, so the vertical bundle is obviously Lagrangian and integrable. So this is one part of the splitting. This H, to describe H, take at every point, take horizontal lift of the tangent space at the point x and intersect it with annihilator of the one form here, one form P. At each point x and P, do this, and then you obviously get a rank 2 distribution at each point, which is transverse to V. And it turns out that the span of these two would give the contact distribution delta. And they're both Lagrangian, and so this is, we can see N has a five-dimensional almost para-CR. And this H, the second H, is almost never integrable unless the projective structure is flat, unlike V, which is always integrable. Now, again, Boris told us that, I mean, we saw it also earlier, that Cartan geometry for projective structures of type SL4 and P1, but here it's SL4 P13, so P13 basically is this form. The reductive part is R star times GL2, and this is the five-dimensional Heisenberg. And so now we're going to again use what we did for Lebrun's construction in this case. As soon as we see there's a GL2, that means we can again follow the same recipe and define the space of all compatible almost complex structure exactly by sort of the same recipe I described earlier. So if we do that, then using the action of GL2, take an almost complex structure and then find the space of all complex structures that turn out to be all complex structures that are compatible with the metric, with the sort of this indefinite metric induced on delta.
And so the fiber here is again the same as before?
Yeah, so again the fiber, this is not quotient, the fibers again are CP1 minus RP1, so the collection of two disks. So this would be a seven-dimensional twister bundle of the correspondence space. So this is the projective cotangent bundle. And it has an induced almost complex structure and a co-rank 1 distribution, which is the sort of pre-image of the contact distribution on N. So here we have a contact distribution, take the pre-image, we get a co-rank 1 distribution. And here, again, we're seeing, like, I put this is the SL4 valued Cartan connection 1 form, but if you're viewing it here on this 5 manifold, this would be the sort of, let's say this would be the H, the annihilator of V, and this would be the annihilator of H, and this together with this would be the contact form. And if you sort of look at this kind of tautologically induced almost complex structure on pre-image of the contact distribution, you would see, again, following the same sort of ideas we explained before, is that the holomorphic one forms in the contact distribution are of this form. So this has to do with the GL2 action, and this is basically this plus, and omega 3 plus I omega 4 would give the 1, 0, 1 forms on the contact distribution. And you would see it's integrable, so we have an honest complex structure induced on this corank 1 distribution. But because this is a pre-image of the contact distribution, the Levy bracket has degeneracy, which is the fiber, the degeneracy along the fibers of this fibration. But it turns out the Levy bracket is degenerate by sort of their higher Lie bracket is non-degenerate, meaning that if K is the kernel of the Levy bracket, then you would see this sort of extended, this Levy bracket going from holomorphic part of the kernel to the anti-holomorphic part of the delta hat into this space. This is sort of non-degenerate, meaning that if there's an element for which all these Lie brackets are 0, then that element has to be 0. So this is the definition of two non-degeneracy. So there is a non-degeneracy, but of higher order in a way. So now we are in a three-dimensional projective structure. We went to a correspondence space, 5-dimensional. It's complex. Its twistor bundle has a two non-degenerate complex structure, CR structure. And we just note that the harmonic curvature of this 5-dimensional, almost para-CR structure arising from a 3-dimensional projective is a binary linear torsion. It's not particular here, it's a binary linear torsion. So it's a linear expression. One interesting question is that there is no characterization of these 7-dimensional two non-degenerate CR structures. Unlike Lebrun's construction, here, I don't know, this is probably a question towards Jan Grigorovich and David Sykes, but they're interested to have this sort of invariant theory of these guys, and it would be interesting, I think, to characterize 7-dimensional two non-degenerate structures arising from, let's say, a projective structure. But so now we want to use these two CR structures and see what we can say about Weyl metrizability. In order to do this, we first need one proposition. So we have this, if you take any section here, so remember this was the almost para-CR structure, this was its twistor bundle. So a CR structure defined by a section of this form, meaning that a section that is transverse to the kernel of the Lie bracket that we had in the CR, two non-degenerate CR, has a canonical CR connection. We can define actually canonical CR connection for CR structures arising as sections of this, with respect to which this sort of relations are satisfied. So we basically, remember, this is the one holomorphic one form that is sort of corresponds to the vertical part of this fibration. So this means that basically this complex valued one form can be written this way, where this is the contact form for two real valued function A1 and A2. Right? This is an alternative way of writing this. Right, so this is actually quite easy. This is a sort of a very straightforward application of Cartan reduction. If you take any section that is transverse to the Levy kernel, immediately you know that the pullback of the one form that corresponds to these fibers can be written of this form. So it's reduced for some complex valued function A0, A1, A2, B1, B2. So as soon as you have this reduction, your 15-dimensional principal bundle is reduced by 2 parameters. So you get a 13-dimensional principal bundle because you're taking a section. And so yeah, it is this principal bundle. You get a principal bundle instead of your nice original principal bundle of the Cartan connection. You get a principal bundle of this part. So this is no longer the reductive part of your parabolic, but something of this form times the same Heisenberg. So if this section gives a CR structure, that means these two coefficients for the anti-holomorphic parts, they have to vanish in order to have an integrable CR structure. So these two have to vanish. And it turns out that you can also kill B1 and B2 by exactly carefully reducing the Heisenberg part. This is sort of, we saw kind of similar things that Boris was talking about. So there is a reduction of the Heisenberg part that basically makes these two components, entries B1 and functions B1 and B2 vanish. So they're like, you see, this is a complex value. This is called, so there are 4 functions here. And by killing 4 parameters here, you can translate these 4 functions to 0. But this is, remember, this is 5-dimensional. So there's still 1 parameter left in the Heisenberg part. And you can also kill that part. So here, so far we've come down from 13 to 9-dimensional principal bundle. And in fact, we can go further to an 8-dimensional by viewing sort of, this is one of the 1 forms in the Heisenberg part. And if you pull it back to this section defined by this relation, then it's also reduced in terms of your semi-basic 1 forms. And you can find sort of this remaining parameter in your Heisenberg part so that this coefficient also is 0. So this way you had reduced your entire Heisenberg group of the parabolic, and also you have reduced your GL2 part to an CO2 part. So you end up with a canonical 8-dimensional principal bundle after 3 reductions, characterized by this coefficient is 0 and these 2 complex value functions. And this defines a Weyl connection for such CR submanifolds arising from sections of this. So this is basically the main observation that will allow us to state the main result, because, so now, in 3D there is a 1-to-1 correspondence between conformal connections in a projective class and 5D non-degenerate CR submanifolds of type N, defined by sections of this twistor bundle. So obviously you can say, this is much weaker property than, let's say, Lebrun's characterization or having like a parallel 2 form. So we just need to assume that take a holomorphic section of this twistor bundle, so it gives a CR submanifold, and we demand that this CR submanifold, the binary quartic, has type N. But this is this is kind of weak characterization, but it's not enough, it turns out. That you need to also impose a sort of a non-degeneracy condition that, remember these are the holomorphic contact 1 forms, that this sort of gadget is non-equal to 0, which is always the case for conformal structures. Because, as you know, CO12 acts there's no distinguished null plane in general conformal structures. Right. So, and this is sort of using the canonically defined CR structure we found in the previous proposition. So to prove this again, it's straightforward. Now, one direction is pretty clear. If you start from a Weyl structure, then you can easily go and show that you would get a CR submanifold of this 7-dimensional, not 2 non-degenerate CR. But the other way, you need to reduce. So start from a projective structure. Go to the 7-dimensional 2 non-degenerate CR structure. Take a section of the twistor bundle. So if you take a section, then you get a CR submanifold. But in general, the binary quartic of such CR submanifold is type 1. It doesn't have any sort of a repeated root. So impose that it has a, but there's a distinguished root always because there's a fibration. So you have to impose that that distinguished root you find in this way, that easily is there, has type n, is repeated up with multiplicity 4. So as soon as you impose that condition together with this, immediately you would see that this sort of holomorphic one form for the fibers is identically 0. It's not like a multiple of the contact form. It's actually identically 0. And this guy that we assumed is non-zero is a multiple of this 4 form where S is defined up to positive homothety. It's a constant defined up to positive homothety. So you can now, because it's defined up to a positive homothety, and this canonically defined CR connection, remember to get it, we have like an 8-dimensional principal bundle. So by normalizing this S, this constant, to plus or minus 1, you get a 7-dimensional subbundle, which defines exactly a Weyl structure of a 3-dimensional conformal structure of Lorentzian or Riemannian conformal. So it's sort of pretty, it just pops up without much effort, depending on the sign of this. So yeah, that's pretty much, that's the proof. And if you relax this condition, there's another branch that, you know, it's not quite non-trivial. It depends on, it can be 0, and if that's 0, I don't know what sort of structure you get. You get a fibration over a holomorphic curve, and it's not that there are tiny amount of them. They're like 4 functions of 3 variables of them. So you really need to assume this condition. Otherwise, there's another branch that I don't really have a good sort of characterization or description of them. So I think I'll stop here. Thank you.
Thank you very much. Any questions? Comments? Remarks? Everybody tired already? We still have 4 more lectures. We're not allowed to be tired yet. Yeah?
So maybe, I mean, the characterization you had before is kind of implicit in a way. I mean, can you use it to derive obstructions against Weyl metrizability?
So that was the last slide, actually. Well, yeah, that's exactly the only thing that is left I want to do for this, to find some obstructions. That because of, you know, the nature of this reduction is kind of algorithmic, but because of this holomorphic section, when you reduce, you want to get like a characterization in terms of its Thomas symbols, so you have to eliminate the choice of section you took. So it's computationally, it's quite algebraic to try to find a sort of a combination because of type n property and eliminate this section, but it's actually complicated a bit, but I'm working on it. So this is the part that I haven't finished. I just wanted to give like a glimpse of.
So thanks. More? Well, okay, so let me thank you again.